You think you understand gravity. You learned it in school. Objects with mass attract each other. The Earth pulls you down. The Moon orbits because Earth's gravity holds it. Simple. Everyone knows this. But you don't understand gravity. Not really. Almost nobody does, because what you learned in school isn't what gravity actually is. It's a useful approximation, a simplified story that works for everyday life, but completely misses what's really happening. I spent 10 years figuring out what gravity is, 10 years struggling with mathematics that didn't exist yet, visualizing things no one had visualized before, trying to solve a problem that everyone else thought was already solved. And what I discovered wasn't just a better theory of gravity. It was a complete reconception of what gravity means. Let me show you where your understanding breaks down. You think gravity is a force, the strongest intuition you have about it. When you drop something, you feel like gravity is pulling it down. When you stand on the ground, you feel gravity pulling you toward Earth's center. Force, invisible but real. Reaching out across space and yanking on things, that's wrong. Completely wrong. Gravity isn't a force at all. I know how that sounds. I know it contradicts everything you've experienced. But stay with me. Because once you understand what gravity actually is, once you see what I saw, everything else in physics makes more sense. Here's the problem with thinking of gravity as a force. Forces require something to transmit them. If I push you, atoms in my hand collide with atoms in your body. That's a force. If a magnet pulls on iron, electromagnetic fields extend between them. That's a force. Forces have mechanisms. They have mediums. They have something doing the pulling or pushing. But gravity, Newton said massive objects attract each other across empty space. Action at a distance, no mechanism, no medium, just instant attraction across any distance through perfect vacuum. The sun pulls on Earth across 150 million kilometers of nothing. How? What's doing the pulling? What's transmitting the force? Newton admitted he didn't know. He wrote that he could calculate gravity perfectly, but had no idea what caused it. He left it as a mystery. For 200 years, everyone just accepted it. Gravity is a force that works somehow, don't ask how. I couldn't accept that. I refused to believe objects could influence each other across true nothingness with no mechanism. There had to be an explanation. Something real happening to transmit the effect. And then I realized something. What if gravity isn't being transmitted? What if there's nothing to transmit? What if gravity isn't a force at all? Let me tell you how I got there. I was thinking about falling. Specifically, I was thinking about what it feels like to fall. And I realized something strange. When you're falling, you feel weightless. You don't feel gravity pulling you. Astronauts in orbit are falling constantly, and they feel no gravity at all, zero, nothing. They float freely. But we say they're in Earth's gravitational field. We say gravity is pulling them toward Earth just as strongly as it pulls us on the surface. So why don't they feel it? If gravity is a force, if it's pulling on them, why is there no sensation of being pulled? Then I understood. They don't feel it because there's nothing to feel. They're not being pulled. They're in free fall. And free fall is the natural state of motion. It's the baseline, the default. When nothing interferes, when you follow gravity freely, you feel nothing. Weightless, zero force. What you feel is weight, what you experience standing on the ground. That's not gravity pulling you down, that's the ground pushing you up. The ground is stopping you from falling, preventing you from following your natural path, and that prevention is what you feel as force. This was the key insight, the equivalence principle. Standing still in a gravitational field feels exactly the same as accelerating upward in empty space. They're not just similar, they're identical, physically equivalent. There's no experiment you can do to tell them apart. If you're in a closed room with no windows, and you feel yourself pressed against the floor, you cannot determine whether you're on Earth's surface experiencing gravity or in a rocket in deep space accelerating upward. The experiences are the same, the physics is the same, and that told me something profound. If gravity and acceleration are indistinguishable, then gravity must be acceleration. Not acceleration through space in the normal sense, acceleration through something else, something more fundamental. That something is space-time itself. This is where it gets difficult, where the mathematics becomes crucial and the visualization breaks down. But I need you to understand this because it's the core of everything. Space and time aren't separate things. They're not independent. They're two aspects of a single four-dimensional structure, space-time. And that structure isn't flat. It's curved, bent, warped by the presence of mass and energy. When you see a ball rolling across a flat table, it goes straight. But if you put a heavy weight on the table and it sags, and you roll the ball across that sagged surface, the ball curves toward the weight. Not because anything is pulling it, because the surface itself is curved. The ball is still going straight from its own perspective. It's just that straight on a curved surface looks curved from the outside. That's gravity. Exactly that. Mass curves spacetime. The sun curves spacetime around itself. Earth moves through that curved spacetime. Earth is going straight. From Earth's perspective, from the reference frame of something in free fall, there's no force, no pull, just straight line motion through curved geometry. But that straight line through curved space traces out what we see as an orbit. You're experiencing the same thing right now. You think you're sitting still, but you're not. You're trying to move through spacetime along the natural path, the geodesic, the straightest possible path through the curved geometry created by Earth's mass, and the floor is stopping you. The floor is pushing you away from that natural path, accelerating you upward through curved spacetime, and you experience that acceleration as weight. Gravity isn't pulling you down. The floor is pushing you up, through curved space. That's what you feel. This is what no one else understood. Not before me. Not really after me either. People learn the equations. They can calculate orbits and predict motions. But they don't grasp what it means. They still think of gravity as a force somehow transmitted through curved space. They miss the point entirely. Gravity is curvature, that's all it is. Mass curves spacetime. Objects follow geodesics through that curved spacetime. There's no force, no pulling, no transmission of anything. Just geometry. Just the shape of reality itself. Let me give you another example. Light. Light has no mass. In Newton's theory, gravity shouldn't affect light at all. Forces act on mass, and light has none, so light should travel in perfectly straight lines regardless of what's nearby. But it doesn't. Light bends around massive objects. We see this. We observe it constantly. Light from distant stars bends around the sun. Light from distant galaxies bends around closer galaxies. The paths curve. Newton's theory can't explain this. If gravity is a force acting on mass and light has no mass, why does light curve? My theory explains it perfectly. Light isn't being pulled. Light is following straight lines through curved spacetime. Light always travels along geodesics, the straightest possible paths. But when spacetime is curved by a massive object, those straight paths are themselves curved. Light goes straight through curved space, and straight through curved space is curved through flat space. We confirmed this in 1919. During a solar eclipse, astronomers measured the positions of stars near the sun's edge. The starlight was bending around the sun exactly as my equations predicted, not Newton's equations, mine. The light was following the curvature of space-time created by the sun's mass. That was the moment the world accepted general relativity. That was the moment they realized I was right. Gravity isn't a force, it's geometry. But even then, even with the confirmation, most people didn't really understand. They thought I'd just added some corrections to Newton's theory, made it more accurate. They missed that I'd completely reconceived what gravity is. Newton's gravity and my gravity aren't different theories of the same thing. They're theories of different things. Newton described a force. I described curved spacetime. Those are not the same concept. They're not even similar. They're completely different ontological categories. And here's why that matters. If gravity is a force, then it has to propagate. It has to travel from one object to another. And that raises questions. How fast does it propagate? What carries it? What happens if you move a massive object suddenly? Newton's theory says gravity acts instantly. The sun pulls on Earth right now based on where the sun is right now. Instantaneous action at a distance across 150 million kilometers. No delay, no propagation time. That can't be right. Nothing travels instantly. I'd already shown with special relativity that information can't move faster than light. Nothing can. So gravitational effects can't be instantaneous either. My theory solves this automatically. Gravity isn't a force propagating through space. It's the curvature of space-time. And when you move a massive object, the change in curvature propagates outward as ripples in space-time. Gravitational waves, traveling at the speed of light, exactly as relativity requires. If the sun suddenly disappeared, Earth wouldn't immediately fly off into space. Earth would continue orbiting for about 8 minutes, the time it takes light to travel from Sun to Earth, because that's how long it takes the change in space-time curvature to reach us. The information that the Sun is gone propagates at light speed as a gravitational wave. We detected these waves in 2015. Two black holes colliding over 1 billion light-years away created ripples in space-time that propagated across the universe and reached Earth, where detectors measured space itself, stretching and compressing by less than the width of a proton. The measurement matched my equations precisely. Gravitational waves aren't just confirmation that my theory is right. They're confirmation that space-time is real, that it can ripple, that it has properties, that it's something, not nothing. You can't have waves in nothing. Waves require a medium. Sound waves need air or water or some material to vibrate. Light waves, electromagnetic waves, they're vibrations in the electromagnetic field. Gravitational waves are vibrations in space-time itself, which means space-time is a thing, a physical thing, a fabric that can wave and ripple and carry energy. This is what people miss. They think space-time is just a mathematical abstraction, a coordinate system, a way of organizing information. But it's not. It's real as matter. Maybe more real than matter, because matter exists in space-time. Matter curves space-time, but space-time can exist without matter. Empty space isn't empty. It's full of geometry, and that geometry is dynamic. It responds to mass, it curves and waves and expands. It has structure, it participates in physics. It's not a background stage where things happen, it's an actor, a player in the game. That's what I realized about gravity. Gravity isn't a thing acting on objects. Gravity is the shape of the stage they're standing on. And the stage isn't passive. The stage bends under their weight. The stage determines how they move. Let me tell you something else nobody understands. Time. When space curves, time curves with it. They're inseparable. Space-time is one thing. You can't curve space without curving time. And curved time means time runs at different rates in different places. Near a massive object, where space-time is highly curved, time runs slower, clocks tick slower, processes happen slower, aging happens slower. This isn't an illusion. This isn't a trick of perception. Time actually passes more slowly in curved space-time. We measure this. Clocks at the top of mountains run faster than clocks at sea level. GPS satellites have to correct for this constantly. Their clocks run faster than clocks on Earth because they're farther from Earth's mass, in less curved space-time. Time literally passes faster up there. Near a black hole, where space-time is so extremely curved that it forms a pit you can't escape from, time slows dramatically. An observer falling into a black hole experiences time normally from their perspective. But someone watching from far away sees the falling observer slow down, freeze, appear to take infinite time to cross the event horizon. Both perspectives are correct. Time is actually passing at different rates, not appearing to. Actually, that's what curved space-time means. And this is gravity. This is what gravity does. It curves space-time, which curves time, which means different locations experience different rates of time flow. Gravity isn't pulling objects through space. It's creating differences in the rate of time, and those differences cause motion. Think about it. If time runs slower near the ground than higher up, then the lower parts of a falling object age slower than the higher parts. The object isn't being pulled down. It's accelerating toward the region where time runs slower, following the gradient in the rate of time. That's gravity. Time curvature. And time curvature is inseparable from space curvature. They're one phenomenon. Space-time curvature. Geometry. No one understands this, not really. They learn the equations, pass the tests, calculate the orbits, but they don't grasp what it means. They still think of gravity as a force, somehow transmitted, somehow pulling. They add the idea of curved space-time on top of their intuition about forces, and they think they understand. They don't, because you can't understand gravity as a force and understand general relativity. They're incompatible concepts. You have to let go of forces entirely. You have to reconceive motion, not as objects being pushed and pulled, but as objects following geodesics through geometry. I struggled with this for years, even after I developed the mathematics, even after the theory was complete. I kept trying to find ways to visualize it that preserved some notion of force. I couldn't. Every attempt failed. The only way to truly understand it is to abandon forces altogether and think purely in terms of geometry. Objects don't move because forces act on them. Objects move because space-time is curved, and they're following the straightest possible paths through that curvature. That's it. That's the entirety of the explanation. And once you see it this way, everything becomes simpler. Not easier. Simpler. Conceptually cleaner. You don't need to explain how forces propagate or what carries them or why they have the strength they do. You just need geometry. Mass curves, space-time. Objects follow geodesics. Done. All the complications, all the questions about mechanisms and transmission and instantaneous action, they disappear. They were never real problems. They were artifacts of thinking about gravity wrong. Let me tell you what else this explains. Inertia. Why do objects resist changes in motion? Why does it take force to accelerate something? Newton said objects have inertia, a property of mass that resists acceleration. But what is inertia? Why does mass resist acceleration? In my theory, inertia and gravity are the same thing. They're both manifestations of how objects interact with space-time geometry. When you accelerate an object, you're forcing it away from its geodesic, its natural path through space-time. The resistance you feel is the object's tendency to follow geodesics. Inertia is just the flip side of gravity. They're the same phenomenon viewed from different perspectives. This is the equivalence principle again. Gravity and inertia are equivalent because they're both about motion through curved space-time. You can't separate them. They're unified in the geometry. Newton had two different concepts. Gravitational mass, which determines how strongly gravity pulls on you, and inertial mass, which determines how much you resist acceleration. He noticed they were always the same, but had no explanation for why. It seemed like a coincidence. In my theory, it's not a coincidence. They're the same because gravity and inertia are the same. Both are manifestations of how mass curves space-time and how objects move through curved space-time. There's only one kind of mass, one phenomenon, geometry. This unification, this simplification, this is what tells me the theory is right. Nature isn't complicated. Nature is simple, elegant. When you find the right description, everything fits together. Different phenomena that seemed unrelated turn out to be aspects of the same thing. That's what happened with gravity. I unified gravity and inertia. I showed they're both geometry. And suddenly all the mysteries dissolved. But here's what still bothers me. Here's what keeps me awake at night even now. I know what gravity is. Curved space-time. I can calculate it perfectly. Predict orbits, black holes, gravitational waves, the expansion of the universe, everything. The mathematics works beautifully, but I don't know why mass curves space-time. I can tell you that it does. I can tell you exactly how much curvature a given mass creates, but I can't tell you why. What is it about mass that curves geometry? What's the mechanism at that deeper level? I don't know. Nobody knows. Maybe there is no deeper level. Maybe mass curving space-time is fundamental, irreducible, the bottom layer of reality. Or maybe there's something underneath that we haven't discovered yet. I spent my later years trying to find that deeper theory, trying to unify gravity with electromagnetism, with quantum mechanics, with everything. I never succeeded. The mathematics never worked out. The concepts never unified the way I wanted them to. Maybe I was looking in the wrong direction. Maybe gravity can't be unified with the other forces because gravity isn't a force. Maybe I was trying to unify incompatible categories. Or maybe the unification exists, but requires concepts I never thought of, mathematics I never developed. I don't know. I ran out of time. That's the tragedy of physics. You solve one mystery and find 3 more underneath. You answer one question and raise 10. The more you understand, the more you realize you don't understand. But here's what I did accomplish. I showed that gravity isn't what everyone thought it was. I showed that space and time aren't what everyone thought they were. I showed that geometry is dynamic, participatory, fundamental to physics in a way no one had imagined. And I was right. Every test confirms it. Every observation matches the predictions. Gravitational waves, black holes, time dilation, the bending of light, the expansion of the universe, all of it flows from those equations I wrote 100 years ago. No one understood gravity like I did. Not because I'm smarter, not because I calculated better, because I was willing to reconceive what gravity is. I was willing to abandon force, abandon absolute space and time, abandon intuition. I followed the mathematics wherever it led, even when it led somewhere strange, and what I found was that gravity is geometry. Mass curves spacetime. Objects follow geodesics. That's the answer. Simple to state, extraordinarily difficult to grasp, but true. You still don't understand gravity. Not really. Because understanding gravity means understanding spacetime, understanding curvature, understanding that motion through space and motion through time are intimately connected, understanding that what you feel as weight is acceleration through geometry. But maybe now you understand that you don't understand, and that's the first step. Recognizing that your intuition is wrong, that forces don't explain gravity, that something deeper is happening. Gravity is geometry. I proved it. And once you see it, once you really grasp it, reality is never the same.